Okay? No? This is okay? I suppose we can start. So, Professor Putinar will continue with hyponormal quantization.
Okay, thank you. We can continue. Thank you for coming. And I'll connect with the previous lecture. Now we move, as you see, from function theory towards Hilbert space. So Hilbert space was present almost all the time in the background of what I was saying, but now is taking the principal role. And I'll remind you a little the Markov transform. Which led to the, if you remember, the understanding of the extremal values for the Markov moment problem. That means when a shade is determined by finitely many moments. And the conclusion was it's only black and white. So what it is about, I start with a matrix point of view. We have a self-adjoint matrix on a finite dimensional Hilbert space. And we consider a rank 1 perturbation of it. Minimax, the basic tool, variational tool in linear algebra, gives us an interlacing phenomenon of the respective eigenvalues. So this is obtained by min-max. Good exercise when you teach linear algebra. And if we take G to be the sum of the characteristic functions of these spectral displacements, we obtain, just with elementary computation, the following remarkable identity. The determinant of B minus Z times identity times A minus Z inverse, Z, let's say, non-real, is equal, as you immediately see, to the determinant of the identity plus A minus Z inverse, the rank 1 perturbation. Now, this affects only one row, so we can compute the determinant exactly, is 1 plus A minus Z inverse evaluated at the respective vector times itself, easy computation, it's a determinant. And what Markov transform gave us, we take what we call the phase of this function, which maps the upper half plane to itself, and it will be the exponential of Cauchy transform of this function G. G, of course, has compact support here, and is entering in the multiplicative structure of this compressed resolvents. In addition, we have the following invariant property. If we compute a polynomial in the perturbed operator minus the polynomial in the original one, and we take the trace, this is precisely the integral of p prime times g dt on the line. Easy to compute. You take, since we have this displacement, what is this? Is p evaluated at the eigenvalues of b minus p evaluated at the eigenvalues of a. Here we have the Leibniz-Newton formula, and we are done. Now, what it is important here, we derive immediately an inequality. The trace of this difference depends only, it's bounded by the subnorm of p prime and the one norm of g. Suppose now that I do a chain of such perturbations, positive, negative, and I add not only one, but infinitely many. What will happen? As long as this G is L1, and as long as this P is bounded, I have a grasp on the sum. So the theorem, this is Lifshitz, and then completed by Mark Krein, says the following. If A is a self-adjoint operator on a separable complex Hilbert space, and K is a trace class operator, that means the trace of the modulus is finite. Then for any function phi of class C1 on the line, we have this estimate phi of A plus K minus phi of A is trace class, and trace can be computed as the integral of phi prime times a function g. G will be of compact support, therefore here we have something finite. And what it is remarkable, this G has a name, is denoted somehow phi or chi of A goes to A plus K, and is called a phase shift. Remarkable invariant formula. Now we went to infinity, and it tells us the spectral displacement under a trace class perturbation. Of course, you have to prove that this is trace class by passing to the limit, approximating the finitely many with rank, finite rank, and so on. Well, this was the discovery of Lifshitz, the physicist, the one with Landau and Lifshitz, who wrote many. And then Mark Krein remarked that you can push this even to unbounded operators, and it gives you a very flexible tool, a very good grasp on the spectral displacement under trace class perturbations. As you know, trace class perturbations preserve the absolute continuous part of the spectrum, and there is a whole theory of Kato-Rosenblum of measuring how the other part of the spectrum is changed. What we'll do today is to exploit this for moment problem in 2D and to discuss the exact analog of this in 2D. And then we'll be able to obtain almost 2D counterpart of the Markov transform we discussed last time. So that's the plan.
So what is that type A to A plus K?
Is the additive perturbation of A by a trace class operator. Is the definition. It's called this function G, which appears in the formula, is called the phase shift. And sometimes in the papers of Mark Krein or Gorberg and so on, you will see this notation. A goes to A plus K, and has remarkable properties, additivity, and so on. So it's a very good tool to encode, again, the change of spectrum under such perturbations. And that's extremely important for a lot of applications. So let's move on. If this works or not. Yes. Oh, thank you. So I'll review a little what I did here, and you remember that this Markov transform was essential for the Dirichlet distributions in probability and many other things. So it's quite interesting now to try to do it in two variables. And for this purpose, 2 is special. So that's the plan. I'll spend some time on hyponormal operators, which are the Hilbert space counterpart of what we are doing here. And then I'll show you the applications, probably after the break, to a lot of potential theory and other interesting mathematical physics, fluid mechanics in particular, questions. So here is what I said before. I repeat with the risk of annoying you, but this is so important that it's better to put it one more time on the screen. What it is so special about the Cauchy transform of a positive measure? You take the imaginary part, that means you multiply with a joint, the numerator, the denominator is positive, and you remark immediately that if you are in the upper half plane, the imaginary part is in the upper half plane. So the Cauchy transform has this very specific property. If the measure has all moments, then along the imaginary axis, this function will have asymptotic expansion, and it's rather well behaved. And for that reason, we add a 1 to control a little to gauge the behavior at infinity. If, for instance, mu has compact support, then this is analytic outside the support, and obviously the value at infinity will be 1. And purely function theory, the Poisson formula, tells you that this function admits a logarithm, first of all, because we are on a simply connected domain. The imaginary part is between 0 and pi. And now we reconstruct the function from the logarithm from the imaginary part. This is the analog of Herlot's formula in complex variables, as you know. So I do that, and I obtain immediately that the logarithm has such a representation. So I incorporate pi into this function, and I get exactly what we have here. This is a rational function of our type, 1 plus Cauchy transform. And this is the exponential representation. G in this situation is between 0 and 1. And we exploited this at the level of moments. Namely, we expanded the moments of G. And obviously, asymptotically, if you want, in the sense of Poincaré, we have this Neumann series. And then we operate formally. And we have this remarkable transform between the moments of a phase function, so bounded below by 0, above by 1, and the moments of the Markov transform, which is a measure. So as you know, these are easily characterized. A Hankel matrix positivity will give you precisely the characterization of this. These are not so easily characterized. But the exponential transform, sometimes, by the way, for formal series is called sure transform, again sure, simplifies and clarifies what constraints these moments of the phase satisfy. And our conclusion, if you remember last time, was that this G is extremal. That means it's only 0 and 1. If and only if this is has a vanish Hankel determinant, is extremal, or if you want, is degenerate as a Hankel matrix. That was our discovery, and this corresponds exactly to the exact reconstruction of shade functions. You cannot reconstruct from finitely many moments a function between 0 and 1 unless has only value 0 and 1, and then it will be on a collection of intervals, not on Borel sets. And everything is encoded into this observation, which goes back essentially to Markov, that the Hankel determinant, the vanishing of the Hankel determinant, determines the extremal solutions. And the matrix perturbation, what I mentioned here, I'll repeat briefly. We have the minimax. We pass to the determinant. This is called, in general, the perturbation determinant. And why it is important? The determinant symmetrizes objects. So when you take the determinant of a quotient of two resolvents, somehow symmetrizes everything. So it's a very good object to look at. And we have what I wrote on the blackboard by the spectral theorem, and the trace formula. Again, the trace symmetrizes things, and the invariance of this is quite remarkable. You don't have to choose a basis. You just take the trace, and is there. And in infinite dimensions, we have, as a conclusion of this discussion, the following dictionary between three different objects. Self-adjoint operator A with a prescribed cyclic vector. You have it there. Functions, the phase functions of compact support with values in 0, 1, any measurable function, and any positive measure on the real line. So that's quite remarkable, because we relate cyclic operators to shade functions, I call them, and two measures. Now, which one do you like to operate with? Depends on what you want to do. In general, operating with functions is easier. Sometimes the Hilbert space geometry brings you another insight. And the measures are wild, as you know. They can be very complicated. So, and the dictionary is exactly this one. I repeat, is the perturbation determinant, the compressed resolvent, and the phase function. If and only if. Basic references for the moment, problem of Markov. If you remember last time I mentioned some 1934-35 articles of Heisenberg and Krein. They put some of them in a book format, which was translated and is there. Then the idea of the phase shift goes to Lifshitz, 1952, so you see is quite late after the 30s. And then it was again Mark Krein who put everything in the proper format and understood the invariance and all the intricate natures of the perturbation determinant. Fortunately translated, but he has many papers on this. And then the book of Gorberg and Krein has quite a lot of discussions about perturbation determinants and how you apply them to dissipative operators, you go into the unbounded case and so on. So this is 1D. We move to 2D. And I'll start with this rather artificial class of Hilbert space operators. So let me write on the blackboard a few things. It's called hyponormal if the commutator is non-negative. What does it mean is written there equivalently. T star does not increase the length of a vector for any x image. Why this class is important? As you probably know, if you want to solve the Heisenberg commutation relation with identity, this is not possible with bounded operators. So, not achieved with x bounded. However, if you relax a little this condition and you don't ask the full identity, but something smaller will have very soon rank 1, or just a non-negative operator, then it is possible. And there we have a rather big class of operators. Now, what are the special examples? Already we encountered one. I think in my first lecture. Take L2 of a positive measure, let's say compact support, on C, and take there the closure of polynomials. You remember we had a long discussion, when is this equal to L2? Not a trivial question. It's a subspace. And take S to be the multiplication by the variable on this subspace. If this were the full space, the adjoint would be what? Multiplication by z bar times f of z if I compute the two norm, z bar doesn't matter, so would be equal. But in this situation, I have to take the orthogonal projection. Let's say P is the orthogonal projection. And obviously, this decreases the norm. So S star F in 2 norm square is the integral of this projection. The projection doesn't increase, so is less than the integral of z bar f of z d mu. But under the modulus, z bar doesn't count. So S star doesn't increase the norm. This is the typical, what is called subnormal operator. The restriction of a normal operator to an invariant subspace. So you see, all this go back to Paul Halmos. Hyponormal, subnormal, so we depart from normality here. Everywhere, in politics, in mathematics. And this is quite relevant. So hyponormal is even weaker than subnormal. The second example is more important. Let's take L2 of 0, 1. With Lebesgue measure. And let's take an operator written in real and imaginary part. What is T star? So what is the self-commutator? X commute with X, doesn't matter. Y commutes with Y. So what is left is only I, X commutator with Y twice. So essentially what we are studying here is pairs of self-adjoint operators with a constraint on the commutator. And now, typical example. Let's take X again. Let's say T here, is multiplication by the variable, the simplest self-adjoint operator. Let's try to produce with Y something which has, let's say, a rank 1 commutator. And I'll do the following. I take a Hilbert transform. That means the Cauchy transform, but pushed to the boundary. The convolution with 1 over t, as you know. So I take a function, let's say age, and I take the Hilbert transform, and here I multiply by age of t, and I put a constant, let's say gamma. age bounded, F in L2. The product is in L2, and as you know, the Hilbert transform is bounded. It's a bounded, the convolution with 1 over t. So this is a bounded transform. And now let's try to compute the commutator between x and y. So let's, yes, is a constant. We'll adapt it as we need. So what means x times y? I multiply by x this quantity. So it will be, I'll write simply gamma t age t age s fs s minus t dt. What is yx? First I multiply f by the variable, and then I do the whole operation. So it's again gamma age of t, and I have age s s f of s s minus t. Let's subtract. T minus s cancels with t minus s. So all in all, in this computation, the commutator between x and y is something like minus gamma age of t, the integral of age s, f of s ds. So what is this? F inner product with age times age, rank 1 operator. So, and it's very different from this one. It cannot be subnormal in general, and is the typical example of a hyponormal operator. Now, why do I mention all this? Because the whole spectral theory of hyponormal operators is based on this model. When we study different classes of hyponormal operators, we want what is called functional models. So rather than working in the abstract Hilbert space, you go to a function space, to a measure, to a Sobolev space, something, and there you import harmonic analysis, complex analysis features, which will pay back and come to the Hilbert space. So it's happening here. Now, I'll leave that on the blackboard and I'll erase this part. So, in a nutshell, what is the spectral theory of hyponormal operators? A few facts. I am just listing them for the connoisseurs here, for people who study Hilbert space, to see how far or how close are from, let's say, normal operators. They are not normal. The resolvent norm is exactly 1 over the distance from the z to the spectrum. Not always, even in finite dimensions, this is true. Normal operators satisfy this, but nilpotent matrices do not. Second, this is Putinar inequality. the norm of the self-commutator is less or equal than the Lebesgue area of the spectrum divided by pi. Meaning one interesting feature, if the spectrum has zero area, this is zero, is normal. So if you take an irreducible operator, you write it in a direct sum of operators, and it has only thin spectrum, for sure is normal. Berger-Shaw inequality. Suppose that the multiplicity of T is finite. This means rational multiplicity. How many vectors you need to span, taking rational functions of T, the whole space. Suppose it's 1. There is one vector which is cyclic for all rational functions. Then the trace of T star T is finite and is less or equal than the multiplicity times the area divided by pi. So very interesting, if an operator has finite multiplicity, the self-commutator is trace class. Not trivial. And why trace class operators, trace class self-commutators are important? Because of the following important formula due to Joel Pincus. He is the founder of the theory and wrote in the 60s, 70s quite a few basic articles on this. Suppose that T is hyponormal and this is trace class. I'll write in short like this. Then there exists g of t, a function L1 compact support in C with respect to the Lebesgue measure, satisfying the following. And now we are getting close to the left side of the blackboard. Rather than taking the perturbation determinant, now I'll take the multiplicative commutator, namely something like this, T star Z bar inverse, T minus W inverse, T star minus Z bar, T minus W. The commutator is trace class. If I commute these two, this will be the identity because this cancels, the other cancels, plus K trace class. Because the commutator is trace class. So Z, W are outside the spectrum. Say again?
Do we know T is trace class to begin with? No.
Of course not. No, only the commutator is trace class.
Otherwise, I was thinking about the third thing. Trace will be 0 if that is trace class.
So only the commutator is trace class. T is not trace class. Cannot be. You will see very soon. A trace class operator has discrete spectrum. The area of the discrete spectrum is 0, so it's normal, not up for us. So the multiplicative commutator is the identity plus trace class. Now, the determinant can be extended into infinite dimensions for this class, and the determinant of this is the exponential of minus 1 over pi g of t dA zeta minus w zeta bar minus z bar for zw outside the spectrum. Sounds familiar. Let's look a little on the left. We have the determinant of the perturbation resolvent, the quotient of the two resolvent, is related here by the multiplicative commutator. The determinant is equal to the exponential of a function which is in L1. Well, there is also an analog of the Lifshitz Krein formula, and this is due to Helton and Howe, Roger Howe, which you know, which says the following. If we take any, this was early 70s, this was late 60s. If we take a function phi of class at least C1, and we take with some proper definition, a functional calculus in T and T star, I'll explain. This will be, the commutator will be trace class, and this will be equal to the integral of the Jacobian of the two functions times g of t, the area. So this is the Jacobian. And this is the analog of the Lifshitz formula. Now, what means this calculus? Take a yes. I'll explain in once. They are not entire functions, smooth functions. So, let's start with phi and psi, just polynomials in z and z bar. I make a choice and put t star in this calculus to the right of t. The same here. I claim that this commutator will be trace class if, of course, we have to assume here, as before, that this is trace class. I forgot to say. We are in the same situation. Now, regardless of how I arrange this functional calculus, maybe you know that if I add a trace class operator in a commutator, the trace will be 0, as in finite dimensions. So, doesn't matter how I define this. And then I can pass to a limit in a proper sense, the Weil calculus or something, and make sense for any smooth function. So the remarkable fact that this depends only on the derivatives of the phi and psi, and the Jacobian, so a kind of commutator between phi and psi, And this function g, which is, by the way, which appears here, it's called the principal function. Now, why this is important? This formula is more flexible than the determinant of the multiplicative commutator and proves that g of t is first invariant under traceless perturbation, behaves well under change of variables, and has all kinds of other spectral properties. So I'll write them here on the board. So I'll simply write this map is functorial in a precise sense that it behaves well under changes of variable. The support of the principal function is exactly the spectrum of t, assuming t irreducible. For a point zeta where the Fredholm index exists, g of t is precisely minus the index, the Fredholm index of t minus zeta. So on the spectrum, this function is extending the Fredholm index, which is a good invariant, as you know, on essential spectrum. So it's a very natural extension, which is functorial and has a lot of properties. And now, what is interesting, and then I'll give you maybe 5 more minutes, just a glimpse of another feature here. This is the beginning of cyclic cohomology. What Alan Kohn started to do with cyclic cycles and so on, this is low dimension cyclic cohomology formula. And it encodes the index formulas you know. If you go into, let's say, Toeplitz operators will encode the Atiyah-Zinger index formula and so on. So it's a deep and important object. Yes, please.
Function and the index formula. There is a relation between Krein function and index formula.
Yes.
This kind of
So the index formula, here we don't have an index there. Yeah, I think that's very welcome. So what is your question? Can you repeat, please?
No, here you connect this GT
Yes.
index of
No, of course. This is, you have to choose different values of phi and psi, and you will have a respective, let's take an example, for instance, since you are asking this. No, it's more complex than that. So let's take the trace of t star to the n and t to the m, or k. Is the Jacobian. So how I compute the Jacobian in complex coordinates. I have to take the derivative of z bar to the n, z to the k, probably there is a 1 over pi here. depends how you define the g. I think there is 1 over pi. My apology. And now the Jacobian in complex coordinates is this derivative with respect to z bar. So is n. This respect to z, so is k. 1 over pi. The integral of z bar to the n minus 1, z to the k minus 1. The other one is 0. G of t of z dA. So what do we obtain here? The power moments of g. So the index is more refined, but if you do just, let's say, simple monomials, you get precisely the moments. And this is our aim after the break. But I want to show you just a couple of other issues here. So it's a very flexible formula. You play with polynomials and you have a lot of information, complete information about the operator.
One more question, sir. Here this GT is explicitly known or this is just its existence?
So here,
In the right hand side function, this GT, what is
so the question is how you define this.
no, G.
G is this function which appears here. The same function.
No, I am asking that this GT is explicitly known or this is just
Good question. Depends on the examples. We'll have quite a few after the break. So depends on the complexity of the operator.
No, as I remember that for Krein test formula,
Yes.
the shift function is can be explicitly obtained in finite dimension. So here,
Let me explain a little. It's a little more complicated, but not much. So we'll take a break soon. So how we compute, how Pincus computed first G. Here is something to understand. So this is another example, if you want, or a hint of the early theory. So we take T, hyponormal, and trace class, self-commutator. And we expand T into real imaginary parts. Let's assume that T is irreducible. Consequence of Berger-Shaw inequality. X is self-adjoint, of course, but has only absolutely continuous spectrum. Non-trivial. This is one of the inequalities which is there. Once we have this, I can represent X as the multiplication to the variable on some, sorry, a technical thing, on a direct integral of Hilbert spaces with respect to measure. That means there is a spectral multiplicity and you have a direct integral, some fibers, and let's suppose it's just L2. But here there is a direct integral on an interval. dt, very important, absolute continuous. Then it turns out that y will be on the direct integral, in this case will be just 1, will be something which commutes with t, a real function, plus the second example I mentioned, the Hilbert transform of, let's say, another function, little k. This follows from the fact that this is also bounded. And let's say, to simplify things, we are on a direct integral. If we are fiber dimension 1, this will be one single function. Let's suppose it is so. With, as we computed the commutator, this will be positive. There is an I here, I think, to make it self-adjoint. Now, the principal function of t, of this t, at the point x plus I y is precisely the phase shift of the perturbation x goes to k times k plus x. So you go on the fiber, evaluated at the point x, everything. So we are on a direct integral, and this evaluated at the point y. So in short, the picture is the following. The spectrum is this. We project. This is AB. On this basis, we have the real part, multiplication by the variable. On the fiber, I have several intervals or a more complicated picture. The value at a point y of the principal function here is the phase shift of the perturbation of the respective localized on the basis x with precisely this term. Now you can imagine that this was cumbersome. You don't see any invariance, you don't see any deep properties here. And it took easily 15 years, 20 years to distill this into an invariant formula which is on the board there. So originally it was just singular integrals computing this. There is of course a function, is a unitary invariant and so on, super complicated. It happens after, I don't exaggerate, 20 years of work, that this is functorial, this function, enters into the analog of the Lifshitz formula and so on. And now we know is the beginning of the cyclic homology. So let's take a break.
There should be tea outside and you can ask me questions privately.
review on my slides what I said. So the basic examples come from singular integrals, the Hilbert transform. And we have these basic inequalities, which are the beginning of the whole machinery. But as I mentioned, it took quite a long time to refine and to reach Hele theorem. By the way, it exists in any dimension. So for tuples of self-adjoint operators with some commutator restrictions in some Shelton von Neumann classes, then there is not the commutator but a multi-commutator there. And the big difference, the measure will not be absolutely continuous with respect to the volume measure. So it's just a distribution. So 2D is very special in this respect. The multi-commutator is important, and it's related to what we did in 1D. We take the multiplicative determinant, the multiplicative commutator, and the determinant will be precisely this compressed resolvent, but now is a doubled argument. So it's a kind of polarized compressed resolvent, and this will be the key to everything which follows. The formula reads as follows, and is on one side we have, let's call it the phase function, the principal function. And on the other hand, here we have a positive definite kernel, minus. So, by the way, this is conditionally negative in other terminology. So it's 1 minus a positive definite kernel. And if we expand this at infinity, we'll have the moments of G. If we expand this at infinity, we'll have, of course, a positive definite kernel, which is not Hankel, but still encodes the properties of T, which were hyponormal, and soon we'll restrict ourselves to rank 1 self-commutator. The dictionary we had before, if you remember, measures cyclic self-adjoint operators phase function, works in this setting as follows. If we work with rank 1, this will be a function between 0 and 1. And here we'll have a hyponormal operator with rank 1 self-commutator. So we have again a dictionary very similar, parallel to what we had before. We replace the measure, the spectral measure, by this more exotic class. And on the other hand, here we have all possible L1 functions with values 0 and 1. That's the inverse problem solved by Joel Pincus in the 70s. So it's not trivial to show that any L1 function produces such an operator. So it's 1-to-1, very important. And we have the Hele trace formula, which is quite remarkable by its invariance. You can pass to smooth functions, and from here you derive very good functoriality properties, naturality properties of G. G is attached to T. So, our story starts with the analog of Markov's multiplicative part. Take a function with values in 0, 1, compact support, and consider it what I'll call exponential transform. This is analytic in Z, anti-analytic in W, and has remarkable positivity properties. It's a conditionally negative kernel. And easy exercise, it will continue separately in each variable across the support of G. So if I fix W, it continues across the support. And this has to do with the continuation of the localized resolvent. The vector Xi is very distinguished, is special in this respect, that the resolvent continuously weakly across the spectrum. So that's the beginning. And the Markov problem now. Take the moments of this shade function. Let's say we work in the unit disk just for convenience, and transform them according to Markov recipe with the exponential. We obtain some, not really moments of a measure, but we obtain a positive semi-definite measure here, a kernel, which depends on G. It's a triangular transformation, if you do formally this. And this is positive semi-definite and has some other properties which are reflected in the hyponormality of T. What are the extremal solutions? Before we identify them with the vanishing of the determinant of this, a finite section of this. Well, this is 0 if and only if the shade function has values only 0 and 1, and the support is what is called the quadrature domain. So we reach here potential theory in heart of the math. We don't obtain all principal semi-algebraic sets, but we obtain enough many to be able to approximate in Hausdorff metric any other domain. So a quadrature domain for analytic functions or harmonic functions is a bounded open set. Domain is a stretch of terminology, it's not connected, satisfying a Gaussian type quadrature for all analytic functions. So if you know a little approximation theory, usually you impose quadrature formulas for polynomials up to a fixed degree, a finite dimensional space. Here you impose the same quadrature formula for an infinite dimensional space. So it's very special. These are the nodes, C are the weights, and you can have higher multiplicity with derivatives there and so on. And the simplest examples, complex variable, take a disk. If you average against the area measure an analytic function on the disk, you obtain the value in the center. That's the Gauss mean value theorem, the beginning of the maximum principle and so on. A disjoint union of disks, of course. More interesting, conformal image by a rational function of the disk has this property. That's an exercise for your students in complex variables. And these are the simplest, but the class is more interesting. And what it is surprising, so you start with no assumption on the boundary. And you put just this quadrature formula, automatically the boundary turns to be algebraic, real algebraic, and the defining function of the boundary has specifically this form. This is quite interesting. So all polynomials here appear. We have one positive square and then negative squares, and their degrees decrease one by one. None of them is 0. So I call this generalized lemniscate. It's similar to the level set of a single polynomial. And this is a feature which was discovered at the beginning of the theory by Aharonov and Shapiro. I'll give details. Not so trivial, these domains, these quadrature domains, are dense among all open sets in the plane. That's an approximation theory result due to Björn Gustafsson, and is quite involved. The proof, you need Riemann surfaces, the Schottky double, and so on. So you don't obtain it immediately. What it is remarkable, and here I wanted to arrive, the extremal situation in the Markov problem on the line, if you remember, was a rational function, was exactly what we had on the board there. The determinant of the quotient of the two resolvents, finite rank matrices. If the Markov transform has this vanishing determinant, then we know it's a quadrature domain, and the exponential transform captures the defining function in the numerator and the minimal polynomial vanishing at the nodes in the denominator. So this is magic, because you start with, let's say, the moments. We'll do an experiment immediately of a domain. You do this exponential transform. It is rational for reconstruction problems. For everything, rational functions are superior. We like finite determinantness. And we read from here the defining function and the denominator. And now this transform has a lot of properties which we used quite a long time ago now for image reconstruction. So at infinity, obviously, is 1. If we start, let's say, with a bounded open set, is superharmonic on the diagonal outside. So it comes from 1 and decreases to the boundary. If the boundary is regular enough, this is exactly close to the boundary, bounded from above and below by the distance. Therefore, if you want to find the boundary, you plot this. If you have analytic arcs in the boundary, this extends analytically. Therefore, if you want to reconstruct something with corners, it will extend above the smooth parts, real analytic, and will be singular at the corners, and so on. And what it is remarkable is not the green function, is not a potential which depends heavily on the domain, but is universal. It's a kernel which doesn't depend on the domain. It's a universal kernel, like the Cauchy kernel. You apply to the function, and then you have automatically this vanishing on the boundary kernel, which comes from 1 to 0. At infinity is 1. So for the disk, easy computation is precisely this. And let's do this computation. It's on the slides. Let's go slowly. Pretend that we don't know it's a disk. But we pretend that we know. We start with the moments of the disk. So what is the area? The 0, 0 moment is the area, pi m squared. Yeah, this is the radius. What is the first moment? I integrate z. And now will be the average of these analytic functions on the disk, so is precisely pi mc, right? I read here the center. Similarly, 1, 0 will be c bar. A1, 1, I have to compute the radius square, And this will be immediately just integration on the disk, polar coordinates, this quantity. So suppose that I give you 1, 2, 3, the other one will be the conjugate. These 3 variables. What do? Take the truncated generating function, so I put the moments into the generating function, and I compute formally the exponential. And I'm looking only at the lower degree in 1 over W, 1 over Z bar terms. 1 comes first, then this is linear, and then I have a product of these 2, only this one will count, if I go up to these degrees. So the coefficients in the Markov transform, so the coefficients of the exponential transform of the generating series are exactly listed here. So these are the coefficients. Well, let's look at the matrix. The first thing, we put them in the matrix, 0, 0, 1, 0, and so on, 1, 1, and check the determinant. The determinant is 0. Therefore, is a quadrature domain of order 1 with exactly 1 node. The factor, the determination of the denominator comes from the linear dependence of the rows or columns of this positive definite matrix. And if I multiply Padet type approximation, if I multiply the transform by the vanishing polynomial at the node, which I founded by linear algebra, and I take only the non-negative part of the series, this is the defining function of the domain. So this is how it works. Now, we apply this to more general domains. We tried on a square, triangle, and so on, and it works magically. We have quite early works on this, and you can approximate with this Padet type scheme shapes. Basic references. Sorry to blow in my own trumpet. Is an early book I wrote a long time ago with Mircea Martin, where all these early theories of hyponormal operators is presented in some detail. Then the starting part of the theory of quadrature domain is this basic article of Aharonov and Harold Shapiro. They showed, for instance, here that the boundary is regular, is real analytic. And then there was a lot of activity. I'll mention some briefly in the remaining time. There is this collection of articles that was dedicated to Harold Shapiro at 75, where you can find a lot of interesting, I think, observations about quadrature domains. So let's see what they are good for and how this Hilbert space dictionary helps. This is Harold Shapiro. He passed recently, and very remarkable mathematician. Super resolution. So we know that this quadrature domains, or in general, the principal sub-level sets, semi-algebraic sets, are determined by finitely many moments. We know that any other domain is not. So the question is, okay, if you perturb a little such a finitely determined moment, how far can you check how far the moments jump? What is the continuity in moments when you perturb and you lose finite determinateness. This is called, in reconstruction problems, super resolution, and it's quite important because you have objects which are special, like, I don't know, rational numbers among real numbers, and they are finitely determined, and then you are close to them, and the question is, can you estimate the decimal representation, the continued fraction, and so on. And this is what I sketch here. I'll not go into the details. So let's suppose now forget about 2D. This works in general. We take such a sub-level set of polynomial and or super level set and the characteristic function. We know that is determined by finitely many moments. Then every measurable function which is close enough to this special one has the bound measures by the closeness by the jump only in moments up to the respective degree. So if I know that the moments are small, then the full gap between the shade and the finitely determined object is small. So there is a technicality here. I'll not go into detail, the multi-index and so on. This is a sketch. So you have this forgetting map, which gives from your objects, let's say, finitely many moments. You know that only at this point, this is injective. As you perturb here a little, this will jump. But then the question is, okay, if you know that they are close enough, the moments, how far are the shapes? And this is super resolution in many, many problems. And the ingredient in the proof is something interesting, namely how you estimate the volume of a sub-level set of a polynomial. This is a classical question. Asymptotically in delta. And there are such rather recent estimates. Big industry goes back to Varchenko, and then Elias Stein work on this and so on. So it's quite well developed. And then there is this 1D work of Lewis on the super resolution of the same Markov problem we discussed. So what I am sketching here is any multidimensional analog of this Lewis and the result is that it works very well, and you can have an upper bound on the gap between the special shape and approximating one, only in terms of the moments. For quadrature domains, I wrote it here. It's quite interesting because only the polynomials which enter into the defining boundary, the polynomials which give the boundary of high enter. And what we saw on the disk works in general. So there is a Padet type scheme which is very effective. Now back to 2D. You take this exponential transform, and what do? You truncate, as we did in the case of the disk, we truncate the formal series. Take it on a fixed degree, n. And then we try to extend it to a vanishing determinant by choosing possibly some other entries. And so you see, we truncate in a rather non-uniform way here. we take out the upper right corner in the matrix. And if we put a condition here, there exists a unique series which approximates this. So long story short, the truncation will have our type of representation. This is the finite central truncation of the operator. And the approximant is rational exactly of this form. So there is here the Padé approximation extended to 2D thanks to the Hilbert space factorization of the exponential kernel. So without this, you cannot understand what is going on. And everything I wanted to put in one line formula. Here is everything what is essential here. You have a quadrature domain defined by this polynomial, special, as you saw. The double Cauchy transform under the exponential brings back the polynomial and the quadrature nodes. So that's essentially what it's all about. And what I showed before is that if you perturb a little this, it's continuous with respect to the data. Just now some special results, and maybe I'll comment on a few or one or two applications. Orthogonal polynomials on the line, as you know, on the real line, satisfy a three-term relation we discussed briefly. What happens with the orthogonal polynomials appearing in this scheme? These are the analogs of orthogonal polynomials. The polynomial vanishing at the finite central truncation. They satisfy a three-term relation if and only if the domain is an ellipse. So quite interesting. A few examples just to show you a little where we are for 2 points. Now we can play the game backwards. Suppose that I give you the quadrature nodes and the weights. Let's suppose they are symmetric. In this case, you prove that there exists a single quadrature domain with this property, so there is a uniqueness. And the exponential transform is this. The denominator has to be this, is a polynomial which vanishes there, polarized. The numerator, simple computation, will be exactly this one. Or if you take a double point, and what is the shape here, by the way? The shape will be a lemniscate. So you have 2 points, and let's say the weights are equal, then for different values of the weight, you get this family of lemniscates with the same nodes. If you have a double point at -1, then again the domain is unique, and in this case it will be a cardioid, a heart. And there are several of this. The double point will be precisely there. And there is a whole jungle of such planar domains. And as you can imagine, they have interpretations of potential theory, first of all, but also physical interpretations. And we'll turn to this very soon. Before, I just wanted to show you something important which shows a little the structure of the Hilbert space object beyond quadrature domains in this dictionary. So, let's take the disk. Unit disk, the old and tired unit disk, is a quadrature domain. The integral of an analytic function against the area is precisely pi times the value at 0. The associated hyponormal operator is obtained by taking the exponential transform. So I take the exponential transform this double Cauchy transform in the z and w variables. And I compute this immediately, will be 1 minus 1 over z times w bar. On the other hand, from my general theory, I know that there exists this rank 1 hyponormal operator, self-adjoint, self-commutator rank 1 hyponormal operator, which is embedded into this formula. If you remember, this is precisely 1 minus t star minus w bar inverse xi, t star minus z bar inverse xi. Now, question for the Hilbert space people here. Find Hilbert space operator which matches this simple rational function. Well, if I expand this in a series, let's look a little. This will be 1 minus the sum of t star k c t star l c over w bar k plus 1 z l plus 1. I have this series. It boils down only to this. 1 is 1, and then we have this, this matching. So what is going on? T star has to annihilate this vector xi. Otherwise, we get higher degrees. So what operator annihilates the cyclic vector xi for t? The shift. So it turns out that t is nothing else than the unilateral shift. Very simple computation. So in this sense, the disk is very special because the hyponormal operator associated to it is the unilateral shift. Nothing simpler than that. Well, it happens that in general, there is a model, a triangular model, which is exactly like this. So we start with an arbitrary quadrature domain. The principal function is equal to the characteristic function of it. And being a quadrature domain means that this cyclic space is finite dimensional. This counts how many nodes you have in the quadrature, the dimension of this space. The minimal polynomial is the restriction of this operator. And then you take higher and higher, you start to populate the Hilbert space with powers of t. So the powers of t star collapse, but the powers of t build more and more spaces. Well, you have these Hilbert spaces. It turns out that there is no gap in the dimension, so there is some injectivity here. And the model is this one. You see, it is very similar to what we have here. Now, these are block matrices, same dimension. We can choose the sub-diagonal to be with a orthonormal basis change positive, so they are all invertible. And there is a simple recurrence relation which reflects the fact that the self-commutator is rank 1. It's just the vector in the upper left corner. So you write this, and you have exactly these conditions. But that's interesting because it means that these are finite matrices. The trace of AK is the same as the trace of the previous one. It's precisely the same thing. And the boundedness is simply reflected into the boundedness of the elements on the diagonal. So, and this is useful. It's instrumental because you have the, the technique, the imagination from the shift, and you bring it to function theory. Now, applications are many. I don't have time to go into all this. There is maybe I should just do a few remarks. There are quite a few physical phenomena in fluid mechanics which are derived by the following dynamics. You have a moving boundary, let's say a blob of fluid moving into another one, so two fluids. And the normal velocity here is inverse proportional to the gradient of the green function of the domain. This is called Laplacian growth. Crystallization is one example. Hele show flow, that means a flow between two very narrow plates, is another one, and so on. The interesting part is that if you start, let's say, injecting fluid in finitely many points, and you drive this dynamics with the Laplacian growth, all the time you will have a quadrature domain. So the quadrature domains are invariant under this. If you start with, originally will be just disks. But then they melt and they go into this. Well, to understand this dynamics is quite interesting. The inverse dynamics, if you can shrink and find the source, is ill-posed. There are ramifications, there are bifurcations. And to understand that is a big deal. And the matrix model is helping in that. Second application. I'll give you references. I don't go much into detail, but it's a fascinating area. Regularity of free boundaries, a specific one. You take a domain omega in C. You consider its Cauchy transform. originally defined outside the domain, analytic outside the domain. Let's assume that this extends analytically across the boundary up to some compact subset. Automatically, the boundary is real analytic. This is a theorem of Makoto Sakai. No assumption on the regularity of the boundary. And we found a proof using the matrix model, the hyponormal operator. Namely, this resolvent extends rather easily, I would say, naturally extends across the boundary, and then you match it on the diagonal with the other depolarized, and you will have a vanishing real analytic function on the boundary. So that was a validation of this whole theory. Of a recent contribution is this separation of the cloud in Thomson theorem. If you remember my first talk, Thomson theorem gives you a decomposition of the closure of polynomial in L2. And you have normal parts and then some Berman space type parts, and I call them the clouds. Well, the question is spectral analysis. How do you separate, let's say, the singular, the normal parts, I call it, is not singular in the usual sense, from the cloud, from the leaf? And the hyponormal operator helps. You can do it. You have to pass to a double limit, which is very normal in this situation, but you can eliminate, you can take out all the spikes and all the embedded point masses and so on, and you have just the round cloud. Asymptotics of the exponential orthogonal polynomials, again, the quadrature domains and the polynomials we derive from this Pardee approximation are special, because if you take the zero set and the asymptotics of the zero set, in general in the Berman, in the Hardy space and all, they will go to some curves, they will go to some reflection of the level sets of green function. Is potential theory, but it's rather cumbersome. For quadrature domain, if you take the proper finite truncation, they collapse to the quadrature node. So and that's a big issue in potential theory, namely the slang there to find the mother body of a domain. What is the mother body is a subdomain or a subset which carries a measure with the same potential at infinity. Packing quadrature domains, this is what I'm doing right now with my friend, Björn Gustafsson. And the truncated moment problem also can be attacked with hyponormal operators. So these are a few the applications, of course, accumulated over quite a few years. What I'm telling you is not of yesterday. And they show that always this interplay between Hilbert space, function theory, potential theory is very useful. This is Björn, my colleague from Stockholm. I think I have more papers with Björn than with Apurva, but we are working hard to match the count. And here are some basic references. We put, let's say, partial observations is not a monograph. In this lecture notes a few years ago, it contains quite a few of the material I mentioned, more recent and applications. Then Gustafsson has, with collaborators, a very beautiful book on Laplacian growth. and has also a stochastic component there. So it's 10-year-old, and I advise you, if you are interested into these applications in physics, is quite something. Then about that time, a little before, these are physicists, we connected with random matrices the Laplacian growth and the hyponormal quantization, as I call it. And this is a collection of articles about the same time, which has to do with Stan Richardson's early discovery. So what, and I'll finish with this. You have this Laplacian growth. And you have this dynamics of planar shapes, which grow, let's say, in time. You compute the complex moments. If n is 0, obviously, if this is expanding, this will be the area, and is an increasing function. If n is bigger than 0, they are constant. This was the discovery of Stan Richardson in the 70s. And so it's dynamics, which has a sequence of independent conserved quantities. Now, for the connoisseurs, they form a Toda 2D lattice. There is a structure there, and it's a Hamiltonian system and infinite dimensional, and you have a lot of interesting physical observations related to the invariance of these quantities in the dynamics. So, thank you very much. I stop here. Okay.
And the final talk is the eigenfunction on Friday after.